Okay, this is problem 3.80 on page 133. Shafts A and B connect the gearbox to the wheel assemblies of a tractor, and shaft C connects it to the engine. Shafts A and B lie in the vertical YZ plane, while shaft C is directed along the x-axis. Replace the couples applied to the shafts by a single equivalent couple specifying its magnitude and the direction of its axis. All right, so I'll let you look at the figure, but let's write down the couple. Let's see, let's call the couple about A, MA, the one about B and B, and C, we'll just call MC. Let's write these down as vectors. So the moment for shaft A, notice that that has a component, that 1,200 pound or foot-pound torque has a component along the z-axis. Most of it's along the z-axis, some of it's along the negative y-axis. In other words, if I were to draw just a part of this, let's say the y-z axis, the moment MA looks something like that. And it has a 20-degree angle. Everybody see that? Mm-hmm. So moments are nothing more than vectors. You can just decompose them along the various axes. For example, this is just a right triangle, so there's a component of the moment there and another component there. Okay. So along the z-axis, what we would need is, well, let's see. We need the magnitude, moment A, I know it's 1,200 foot-pounds, but we'll put that in a second, multiplied by, let's see, this would be the cosine of 20 degrees in the z direction, which is k, and then minus the sine of 20 degrees in the negative y direction, which is j. Everybody see that? So we just need to replace this with 1,200 foot-pounds. I don't like the idea of using pounds feet. I disagree with that. So if you don't mind, take 1,200 times cosine. Well, better yet, let's put j first. What is 1,200 times sine of 20? What do you get for that number? Just give me a couple of decimal places. So 1,200 sine 20.
410.42.
410.42 in the j direction, thank you. How about in the k direction? 1,200 times cosine 20.
1127.63.
Thank you. So that is a vector representation of the moment applied to, this is probably a differential, right? Because you got shaft power coming from the engine and torque coming out the two axles. And of course, the angle of those axles, since you have a suspension system, they might move up and down. How about the 900 foot-pound torque? What shall I do with that? You tell me. It lies in the YZ plane. Will it have positive or negative components, say, on the y-axis?
It will have negative components.
How about on the z-axis? That's correct.
It will have negative on the z.
So, right, so both of these are going to be negative. So it would be 900, because of course we need the moment B. And now the z-axis would be negative cosine, 20 degrees, and negative sine, 20 degrees for the y-axis. Make sense? So now I just need 900 times cos of 20 degrees. What do we get for that? Well, give me sine first. 900 times sine of 20 degrees. We'll put them in proper order. (900 times sine of 20).
307.82.
Thank you. How about cosine 20 times 900?
845.72.
845.72, and that's in the k direction. All right, anybody want to tell me what to write down for the moment of C?
For C, it would be, so 840.
840 what?
840 pound feet. Or you said foot pounds.
Direction. Give me direction.
840 in the I direction.
That's it. All these are foot-pounds, so I won't bother writing down those.
Okay.
Okay.
And then
And it doesn't have any component in
Yeah.
any other direction.
That's right, so that's it, right? Now let's be careful here. Is it in the I direction? I know it lies along the x-axis. Use your right hand.
Oh, it's in the opposite direction.
Ah, it is, it's in the negative I direction. What about B? Did we make a mistake there too?
No. Wait, yeah, we did, 'cause it's in the positive Z.
Both of those are positive, aren't they?
Wait, the Y is
No,
positive
that's my
on B?
left hand.
It is.
'Cause I thought it rotated down.
Use your right hand.
Oh, and then it would be pointing up.
Exactly.
Okay,
So if we were to draw
because you're angled
Here, I'll show you.
down. This side's angled down, but this side's angled
The
down.
shaft down
Oh,
like
it's actually
that.
angled upwards.
right? But the moment is like that. See that? Okay, so I made a mistake there. It should have been positive, not negative.
Wonder who said that.
Okay, so now I think we've got everything squared away. All our directions are correct. And so now, an equivalent couple or equivalent moment, they say specify a single equivalent couple, and they're using the term couple and moment interchangeably. They're not trying to get us to calculate some force at some distance, okay? The equivalent couple would simply be the sum of these. We just need to add them together. That's easy. So the equivalent couple would be negative 840I. Then all we have to do is add components. For the J component, we add these two together. Let's see, basically pull that out, that'd be 40 point. So we're taking, let's see, I stuff on my shirt. 410, the difference is what, 103? I'm thinking right?
Wait, for J,
Yeah,
that's
for J.
Y, correct? Aren't they going the same direction of J?
Positive, negative. Remember, we discovered we wrote down MB wrong. They're both positive.
Isn't J the Y direction?
J is the Y direction, yes.
That doesn't make sense. That doesn't make sense in my head because this is here.
Let me draw on the board what you're drawing in the air with your
This is
hands.
here. So,
What we just discovered is that one of the moments actually looks like that,
oh,
right?
wait,
And then the other moment
that's Y.
at A
Okay.
looked like positive K, negative J, it looked like that, didn't it? So is it possible that Y components would tend to cancel? Yes, because one has some positive Y components, the other one has some negative Y components, so sure enough, turns out that the bigger torque, the one on this side, the 1,200 foot-pound torque, is going to cause a component of the resultant that is in the negative J direction.
Okay, that makes sense now.
Good question. All right, so if we add these two together, let's see, I'll just do that at the board, I guess. 5, 7 is 3, carry the 1. 8, 5, 13, carry the 1. 7, and 1, 9. Positive, if I did it right in the K direction. Did I do that right? And these are all foot-pounds. All I'm trying to do is add the K components together.
For J, I got negative 102.6.
Did I mess this up?
Thanks.
You said 102.6, Stephen?
Yeah.
I got that as well.
Okay. Yeah, I wasn't thinking right then. How do you get 0.6? Taking 0.42 away from 0.82.
I think it might be some rounding stuff because.
Did you get 0.4? Yeah, because this is negative.
What's that?
Did everybody get 102.6? Okay. Whatever it is, it's the difference between these two, right? 307.82 minus 410.42. So all we're doing is just adding up components, that's it. Did anyone verify this number then? I'm having trouble with the board with math. Okay. So the question is, what's the magnitude and direction of its axis? Well, to get the magnitude, we'll have to take the square root of the sum of the squares. So 840 squared and 102.6 squared and 1973.35 squared and then square root. That'll give us the magnitude of the resultant couple. And then we'll figure out the direction. How will we figure out the direction? Well, we'll come up with a unit vector in this direction, right? So, go ahead and add the square root of the sum of the squares together for me if you would. Yes, you're right about the 0.6, I wasn't thinking right.
How is the K, oh, never mind.
That's that.
You want to have a number?
It is 2147.15.
Do me a favor. Well, or I'll do it for you. If we were to simply add 1,200 and 900, it'd be at what, 2,100? Then if we add 840 more, we'd be at 2,940. If you simply took the sum of all the moments applied, you get 2,940, which is different than this moment, isn't it? Because there we're not taking into account direction. We have to take into account direction, this IJK stuff, when we add moments together, just like we do with forces, okay? All right, what about the direction? Well, now, with this magnitude, what we need to do, let's get rid of all this, we don't need it anymore. What we need to do is take the moment vector itself and get the unit vector direction. So we'll take negative 840I minus 102.6J plus 1973.35K and divide it by the sorry, I didn't write that out. Divided by the magnitude, 2147.15. Both numerator and denominator are foot-pounds, so they just cancel out. This vector has units of foot-pounds, and the magnitude has units of foot-pounds. So all that I just wrote just goes away. So take 840 divided by 2147.15. What do you get, please? We'll calculate each of the components. Obviously, the largest component is in the K direction.
Um, 0.39. How many decimals did you want?
Yeah, two more if you got it.
1, 2.
That's fine. Okay. How about the J direction? It'll be a lot smaller than that.
I got 0.5248.
0.5?
Yeah.
No. No way. 102.6 divided by 2147.15 is not. 102.6 is not.
Do 102.6.
Yeah.
I got negative 0.04778.
So if I'm taking four significant figures, that'd be 0.0478.
And then the last one
Yes?
is negative 0.91.
It's positive, right?
It is 0.919.
One more decimal place if you got it, please.
0.05.
Okay, so
What?
1. So that's the direction. That is the direction of the equivalent moment to all those three. Most of the resultant vector points in the K direction. That's the Z-axis. Okay? Any questions about all this? So what does that mean for this transmission? What does that mean for this differential? Well, that means it's being torqued pretty hard. That makes sense, doesn't it? Because the differential has to take the reaction forces or provide the reaction forces from the frame out to the wheels so the wheels can drive the thing forward. In fact, here's another question for you. Do you think that something like a backhoe, okay, so I'm a two backhoe family. You know, you've heard of two car families. I'm a two backhoe family. One of them runs and one of them is a pile of scrap that I can't bring myself to get rid of because it seems like there's so many darn useful parts on it. I'm gonna build something out of it someday. Well, so I'll tell you that my backhoe generates about 34 horsepower or so, and my car generates a little over 100 horsepower. Which one do you think applies the most torque to the wheels when it first starts off? Backhoe by far. That's right, because it's geared down so far that it increases the torque. Now, of course, in a drag strip race, my car is going to smoke it, but not initially, right? Because initially there's so much torque on the backhoe, I can actually raise the front of the backhoe off the ground, okay? Even though it's fairly weak engine. Somebody had a question. What was the question?
It says specify its magnitude and direction. Could that not be done with the
Yes,
the
we can have more
components?
fun. We can have more fun. So there are the components. You mean, would this be adequate?
Yes, because
It's
the
okay.
amount and the direction all in one.
It's okay, but I like this better because that is just the pure direction. And they did ask for the magnitude, which suggests they want something separate for the direction. However, I thought you were going towards this. Couldn't we calculate these? Yes, we can. Let's do it. Right? We could get theta, x, y, and z. In other words, we could get the direction angles. And that was back, let's see, where are the equations for that? That's back in, I think, chapter 2, if I remember right. And I think your author referred to that section as direction cosine. Yeah, here we go. So go to page 58 and look at equation 2.3. Where they have written that the cosine of theta x equals dx over d, but they were talking about forces. So you might be thinking, well, these are just force components, right? A force component in the x direction along with the magnitude of the force vector. We can use this for moments just as well as we can for forces. So we can get the angle of the resultant moment off of the x-axis, the y-axis, and the z-axis just by doing this. So for example, theta x would be the inverse cosine of dx. So the easiest way to do this is just to use the unit vector, though we could use the moment vector itself. Notice we've already so-called normalized it. In other words, we've gotten percentages for each of these axes. We've already taken dx over d. That's what this is, right? So we need the inverse cosine is negative 0.3912. What do you get when you take the negative, or the inverse cosine of negative 0.3912?
$113.03.
And so that is the direction off of the x-axis. So the x-axis comes off something like this. And so what this says is that the angle of the resulting vector measured off of the x-axis is, how much did you say, 101?
113.03.
Okay, notice that it has a negative component. That makes sense, right? In other words, the vector, if I were to extend the x-axis backward, it's something like that, right? 113.3, you said?
Yes, sir.
Now, this is in a plane, and this plane can move around, right? I don't know where that plane is yet, but we're going to find out. Because the next thing to do is say that theta y is the inverse cosine of negative 0.0478. What do we get when we do that?
You get 92.74.
So 92.74, that's the angle measured off of the y-axis. So 92, that means this vector is gonna have to go down that way quite a bit. Right? So although it's difficult to draw, now that angle is still 113.3 degrees. All that's happened is the plane it was in came down. See that? And I should be making this a double-headed arrow. Because you know that the angle off the y-axis to this vector is 92. Well, actually, it should be farther. It should be below, right? Something like that. So let's see. Now you can really see the 113.3 degree angle. Well, let me put it down here so it makes more sense. So off of this axis, that angle, 92.74 degrees. And you know where this is going. Theta z is the inverse cosine of 0.9191. What do we get when we do that?
23.21 degrees.
So the last angle in here, 23.21 degrees. That makes sense to everybody? Now, we usually don't like to have, well, that's not true. Yeah, that works. That's fine. Any questions about all this?